So, welcome to this first and hopefully not last, certainly not last, joint Simon Center and Mass colloquium. The idea being that whenever Simon Center will have a workshop, we'll try to co-opt one of the organizers or distinguished visitors to give a talk that hopefully will be attended by the Mass department as well, so that we know more about what goes in the other building and you know more about the people who sit next door. Today, for the first Simon's Center and Mass colloquium, very, very pleased to have Andrei Okounkov from Columbia University, who will talk about deep waters of quantum cohomology. For the people in the Mass department, if you don't know, there is a conference going on at Simon Center right now, in particular in honor of 60th birthday of Pavel Wigman, who is taking a seat over there. So happy birthday to Pavel, and we welcome Andrei.
Of this event celebrating, maybe it's a little too loud, so celebrating the science and Pavel's contribution to it, and from the organizers I'm giving this talk on some topics related to his research, and so I hope you will connect various things to which Pavel contributed over the years, and so that will be my goal is to have a slightly relaxed talk in which various topics dear to Pavel's heart pop up. So we'll start with quantum cohomology. And what's quantum cohomology? It's really quantum product in the cohomology of some, say, algebraic variety X. And the way it's defined, that suppose I have, this is my X. So there'll be a lot of pictures which look like a square and then something circular in it. They will mean different things in different instances. So this is a picture of X. And I have three cohomology classes, which I'll represent by the Poincare dual homology classes. So I'll draw three cycles in X. And I want to quantum intersect them. Means I want there be some, let's say, these are Poincare dual to alpha check, beta check, gamma check. And the ordinary intersection product would have been alpha cup beta inner product gamma. That's one way to write it. And now I want to replace it by a new quantum product. And this is a sum over all holomorphic spheres in X. So X, say, complex algebraic variety. So I'm summing over all holomorphic spheres that meet my three cycles. So spheres, let's call it S. And I'm summing over all this S with a certain weight, which is usually in physics, whenever we sum, we have to put a weight which is exponential minus a certain energy. Means here it's minus the area of this sphere, that is to say integral over S of some area for. Yeah, this is supposed to represent holomorphic spheres. So maybe I'll draw it more like a sphere. Okay. So this is a thing that the structure constant of this new multiplication takes values in functions. So this is a function. This thing is a function on H2 of X, where this area form lies. And if this thing becomes very, very positive, then the contribution of every surface of non-zero area is suppressed, and I only get, so this thing, if this goes to plus infinity, then it just goes to the ordinary cup product. So it's because it has to be the case that there has to be a holomorphic sphere of zero area, and that is a point, and therefore we're really counting triple intersections. And so, how is this related to Pavel's work? Well, I mean, this is obviously for physicists, that's a very specific, very special supersymmetric sigma model, and I need not say more. But for mathematicians, this is one maybe slightly surprising fact about it, that this defines not just commutative product, which is obvious from this definition because this alpha beta plays symmetric role, but the key point was supercommutative. The key point that this is associative.
Is your convention that the round inner product means cut product?
Exactly, yeah.
Evaluated against the fundamental side?
That's right, that's right. That's the standard one, yeah.
So the last thing is really a triple cut product.
Yes, exactly. That's the integral of alpha, beta, gamma over x. And you see, whenever we have, so we're not going to meet varieties without cohomology. We'll just think of the cohomology as commutative. And then whenever one sees a commutative associative ring, one has a maximal commutative family of operators, just given by operators of multiplication. Right? So there is a map, which is, you think it's silly. So now I'm going to draw another square, which represents. So this represents all algebraic varieties. Maybe should make it more fuzzy. So I'll say algebraic varieties. And there's a map which goes to quantum integrable systems. I'll denote this map maybe QH for quantum cohomology. And the association is that I was told not to use this board, but is this board okay? The association that the ring, the commutative ring, I associate. So if I
think not, because the issue is whether they can get it on the screen. So
right, and I'll say it in words. Then the operators I consider are the operators alpha star. These are operators, they commute. And they form a maximal commutative. This is the subalgebra in endomorphisms of the cohomology of X. And it's a maximal commutative subalgebra. This is true for any commutative associative algebra. This is just elementary factor, somehow nothing to it. So,
why is it maximal?
because you just apply, well, the commutative associative was 1. Because, right? So you think, well, that's silly. Right? We're not quantum integral systems. There's a lot more to quantum integral systems than just commuting operators. In commuting, there's we don't want just commuting operators. We want things with extra structure. And of course, this is not this is maybe the perfect time, but certainly I'm not the person to discuss what's a good quantum integrable system and what's not. So I'll just want to say that recently there's been a great progress due to the work of Nikita and Samsoni, the work of Nekrasov and Shatashvili, in understanding which algebraic variety X going to produce. There's some particular corner here that we like. Maybe I'll draw it. I'll explain what it means. So there's some particular, among all possible definition of quantum integrable system, there's some particular corner we like, and that has to do with solutions of Yang-Baxter equation. I'll explain in a second. Since this is supposed to be a talk for everybody, I'll explain to you what the Yang-Baxter equation is. And as I said, that there is a pretty good understanding of what are the algebraic varieties that through this correspondence we're going to give you something that of some quantum integral system of this type. So it's slightly diffuse. Maybe it's there's some. It has to do with the fact that you can take R matrices in different representations. So which representation are allowed? This is somewhat diffuse. But there's a solid core. There's like diffuse core, which are this moduli of vacua, moduli of Suzik H vacua. This is slightly diffuse, but the solid thing are the Nakajima varieties. As I said, this understanding came through the work of Nekrasov and Zhitashvili. And work of other people inspired by them. So, so now I'm not going to describe what this is. Maybe I need space here. And this is of course not the first time something like this has been found. There's somewhere here, on some kind of island connected to this, sit like the flag varieties. And those, by the old work of Giventhal and Kim, they go to Toda lattices. But so today I was going to talk about the two examples I was going to discuss today are the first textbook example, which is here, is maybe I need some color here. Maybe this is maybe here. We'll call that will be the spin 1/2 XXX spin 1/2 XXX magnet chain. And this, in this world, this comes from the cotangent bundle of the Grassmann varieties. So this is somehow, this would connect to the old work of Pavel on integrable chain associated to representations of finite dimensional Lie algebras. But more interestingly, you can think in this world there is room for infinite dimensional Lie algebras. And in particular here, so here the corresponding Lie algebra is SL2 or GL2, say. Here in this world, there is room for infinite dimensional Lie algebra, such as GL1 hat. And this it corresponds to instanton moduli spaces on R4. And this, in this world, this is going to go, the corresponding point here, is our quantum integrable system that include and start the first case of this thing. It's the quantum intermediate long wave equation. That stands for intermediate long wave equation. And that's an integrable hydrodynamic equation on quantum one, on which Pavel and collaborator in a similar equation, they worked a lot, and that has been one of the very kind of recurring themes in his work. And so so that would be, and we felt like, and so maybe you can say, well, what is it about this equation that might be new to these people, and well, maybe at the end of the lecture, I'll get to something maybe hopefully new. It's a formula that Nikita and I a long time ago proved about the actual finding a spectrum for this quantum intermediate long wave equation. So if I get there, that will be the end of the talk. So now I should explain what is this world? Well, Young-Baxter equation is an equation for an operator. The operator acts in a tensor product of two spaces. Maybe you call it V prime. So maybe we'll denote this operator V prime. Depends on the parameter U, and it acts here. And the Young-Baxter equation is an equation on. So it's one of the equations written as you enter the building. That these are the some of the most important equations in mathematics, and that certainly belongs there. And that's the equation reads, this is an equation now in the triple tensor product that you have. If you consider the tensor product of three spaces, then the equation you write, and you act by this operator in the first and the second factor with variables u1 minus u2, in maybe 1 in the third, u1 minus u3, u2, 3, u2 minus u3. And that's equal the other way around. Sorry, I have trouble writing 3 here. And so the particular solutions that we're going to look at, they'll be of the following form. So all of this will be modules. All of the spaces will be modules.
There's some U's on the right-hand side.
Yeah, the same use. It's just, yeah.
You're going to restrict yourself to difference variables?
In this talk, yes. So for this particular solutions, we will consider all of this will be modules over some Lie algebra G. And the particular solution we want is that the start of like this. That start R of U starts as 1 plus sum over the dual basis of my Lie algebra, E alpha tensor E dual alpha over U plus some series in U. And so, and there's a general theory if you start this for any semi-simple Lie algebra, this solves the Yang-Baxter equation up to the order 1 over U, and there's a general theory of how to continue this solution. But then if you do this, then there's a following absolutely general procedure how to produce a quantum integrable system that goes like this. You take any element, take and fix any element G in the group G, which this Lie algebra, this is Lie algebra of some group G. So we're going to fix, and then consider the trace. Maybe we'll call it T W of U. This is the trace. You take a tensor product of some auxiliary space. We consider a tensor product of some auxiliary space W and the space we're interested in V. And you take the trace in W of this element G acting there and not acting in W. And then R W V U. This for fixed G, this commute for all W and V, W and U. This is an operator. This is an operator in V. Once you've taken a trace over W, this acts in V, and they commute. Okay. So you get so what this gives a family of commuting operators parametrized by this variable G here. And what is supposed to remind us? It's supposed to remind us here we have a family of commuting operators parametrized by this vector space. But really, we should be thinking not of this vector space, but it's here double. If you think of omega, so the main identification proposed by Nekrasov-Ashadashvili is that you should think of G, we should identify maximal torus of G. That should be here. This thing is not going to change if I replace omega by 2 pi I integral cohomology class, because then will be this exponential is not going to change. So this will be h2 of x c modulo 2 pi I h2 of x z. Is that clear? This function, if I shift my omega by 2 pi I integral form, the integral is going to be an integer then over any holomorphic sphere, and so this is not going to change this thing. This one?
The operators in V.
Yeah. You have an operator in the tensor product, and you take the trace over one factor. You get an operator in the other.
So it's the trace of the product.
This was an operator in here, and we've taken a trace over one factor, the auxiliary factor, and then it remains an operator in the other factor.
So you're taking the composite of these two operators.
That's right. This is a product of two things. Right.
And then taking trace.
You then taking trace. That's right. So for that, more questions?
V, sub V, because it's operator in V. V.
Well, this is an operator that acts in all V. This is an element. This is an endomorphism of V for all V. There's some kind of abstract operator that is an operator that depends on W, and it acts in all V. No, I mean it's an element of some Yangian. It's an element in the Yangian, and there it depends on W. It doesn't depend on V. More questions?
The last line.
What?
Just the last line. This is a desiderata to find the G.
That's right. So this is a part of requirement that this group G should be such that its maximal torus, where we take this element G, is naturally identified with the space. More questions? I should say that this is for finite dimensional Lie groups G. This is an extremely developed area, and in particular for finite dimensional G and any representation whatsoever for semi-simple G and any representation whatsoever, there are a spectrum of this. A spectrum of this in any V is described by beta equations, which are called beta equations because for general G they were written down by Wigman and collaborators. So by beta equations. Right. So this is a general feature. This is a general outline of the correspondence. And so now I want to talk about. So it has many unexpected features, but two unexpected features I want to point to specific. Yeah.
Can't really relate the quantum cohomology expression to the solution in a directive way.
It's not immediate. It's not obvious. It's a miracle.
Well, what's the statement though? I mean, what's the relationship between the two boards? Actually?
Yeah, I'll give this. So the relation. Okay. So the relation is that if you want this algebra is naturally isomorphic to that algebra. To the algebra of these operators, naturally has a morphism of this. But there's much more. I'll explain that. It's made it so far that the algebra of these operators is naturally isomorphic to the algebra of these operators. I mean, they have two commutative algebras, but they're naturally isomorphic.
So given an X, are you actually asserting there's a uniquely defined Lie algebra associated with it? And
Yes.
So here you said what's maximal torus and
Yes, exactly. You can tell what the roots are. It's all somehow, yeah. For any X in this corner, yeah. Okay. So.
If you have X, you have to produce the Yang-Baxter.
That's right. Exactly right.
G.
And well, G will come out of it. If you have a solution of Yang-Baxter, then if you just look here, you have your Lie algebra.
Is G always semi-simple, or?
It's semi-simple, but very infinite dimensional in general. Yeah, I mean, depends what you're calling. It's not a finite dimensional Lie algebra. There's no new finite dimensional Lie algebra. That'd be pretty surprising. Yeah.
Gives a family of commuting operators. What gives a family of commuting operators?
This construction associates to G
What construction?
this. It's a formula. It depends on G. And the statement that you fix G, then whatever you plug in for U and W, these are going to commute. And so as operators in V, they will commute no matter what W and U you take. Yeah, right? So, but this will, for different G, this will be different commuting operators.
Because of this equation.
Yeah, because of the Young-Baxter equation. The simple corollary of Young-Baxter equation. Very simple one. Okay? So now,
Commute for all values of U, so you
yeah,
the
that's right.
coefficients of expansion.
So there are two things. So two things I want to discuss, and one is you have some natural structure here. You might wonder, or on one side, you may wonder what's the meaning on the other side. And the questions, the natural structure on one side, here somehow the Young-Baxter equation is all somehow about tensor products. Here you have Young-Baxter equation is somehow about tensor products. And of course, it's one question is where this goes on this side.
What structure is simple over here?
I'm just saying, here, you always talk about tensor product of things. And so, in particular, if you think of V as cohomology of some algebraic variety, that what should be a structure on X, so that to correspond to tensor product. That's one question I want to discuss. And a second question, here on this side, there's something called, I hope I have time for this, there's something called quantum differential equation, or quantum connection. Quantum differential equation, which is a structure strictly stronger than just commutativity. It's stronger. It's a stronger structure. And so what does it correspond on this side? So the two questions are the inverse of the tensor product under this correspondence and the push forward of the quantum differential equation under this correspondence. Okay, so we'll start with the first. And the first is actually kind of easy. So by definition, so one can say definition is that, well, this is I'm staying in the world of, say, Nakajima varieties now, or this modulus. So one say that X is a tensor product of x1 and x2 if all of these varieties are holomorphic symplectic, if there exists C star action on X, or U1 action on X, preserving the holomorphic symplectic form, holomorphic symplectic omega, such that the fixed points are x1 cross x2. So maybe while it be easier if I give an example.
X is always compact?
No, never compact.
But in this previous discussion,
Yeah, it's all
against fundamental cycle, that's what.
invariant cohomology well defined. It's the entire discussion is in fact taking place in some invariant cohomology, which the fixed point for some element is compact.
So it's a non-compact hypothetical manifold?
That's right. Yeah. So I mean, when I wrote T star of Grassmannia, that's a typical example. Okay, so
Their rods are they Kac-Moody type or?
no, general beyond Kac-Moody. They contain Kac-Moody. General beyond. So so examples. The first example is this T star Grassmannian. Maybe I'll call it TGN. That's the disjoint union over all K, the cotangent bundle of the Grassmannian of K plane inside an n-dimensional space. Okay, all possible subspaces in n-dimensional space. And my C star, I will take the following form. I will take n1 copies of, I'll spell it like this. n1 copies of this, n2 copies of this. And what are the fixed points? The fixed points, it means I'm asking for subspaces that if I scale by this, they remain the same. Well, that has to be that it's a direct sum of a subspace here and a subspace there. So then TGN fixed points are TGN1 cross TGN2. Well, is that clear? So if I'm scaling first and one variable and I want my subspace to be invariant, it has to be direct sum of something spanned by, it has to be spanned by, if you have an operator and you have an invariant subspace, and it's spanned by eigenvectors. That is to say, space has to be spanned by some subset here and some subset here.
This definition is not unique somehow.
It's not. You see, you can require, to make it unique, you can require it to be holomorphic symplectic in a strong sense, have a unique symplectic form. At least, well, yeah.
Start to be trivial.
Okay, right. There's some. No, you can look. This is supposed to be. So that was the first example, and the second example, if I take Mn to be again disjoint union over all charges, this is our UN instantons. Okay, we have the father of instantons, and in this audience, I'm very humbled to be talking about instantons in this. So UN instantons of any charge, K may be called. This is analogous to this. K goes to be 1, 2, whatever. And we take it modulo, not all gauge transformation, but gauge transformations trivial at infinity. So we only mod out by gauge transformation and go to 1 at infinity. And then there is a residual action on this space of constant, UN, x by constant. Gauge transformations. And I can take that same torus in here. And then something that commutes, if you have a connection that commutes with constant gauge transformations like this, then it has to be the case that the connection is reducible. It's a sum of 2. So again, the fixed points stays the product.
Instantons are on R4? Or?
Instantons are, on R4. Well, let's say C2 square, because the actual moduli, what I'm talking about here, are not this moduli, but a certain partial compactification that's by torsion-free sheaves. So that would be somehow better statement. This is a partial compactification of that. If there's something you add as the instanton shrinks to 0 size. And maybe I'm not going to describe it in general, but M1 bar, this is just the Hilbert scheme. Scheme of points. C2. And then that is to say, again, another box. It's a box after box. So it's my picture of C2. And the Hilbert scheme of points is parameterizes unordered collections of points. But what it remembers are not just points, but it remembers the polynomials that vanish on this point. It really parameterizes the ideal of these polynomials, meaning that if one point approaches another, then it's going to remember the direction at which it approached. Because if one point approaches another, then there was there was a linear polynomial here that vanished on these 2 points. And if it approaches along some direction, this will remember that direction. Okay? So, so maybe, so in particular, so maybe well before I erase this board, there is a strong geometric reason why people are interested in quantum cohomology of things like Hilbert scheme. Because if you think of, oh, maybe I'll write it here. Why do people care about quantum cohomology of this, or of instantone moduli spaces, or of Hilbert schemes? Is because if I'm studying, if I'm thinking of if I take a product of, say, C2 in a curve, say P1, just to take a product of that. And if I'm looking for a holomorphic curve of some higher genus in here, C, it's a holomorphic curve, then I can view it as looking at, we're looking over various points in P1, I can look at the cross sections. And this curve in threefold I can view as a higher genus curve in the threefold. I can view as a holomorphic curve in the Hilbert scheme. And so quantum cohomology of the Hilbert scheme is really related to counting curves on threefolds. And similarly, quantum cohomology of higher rank objects is similarly related to theory of sheaves on threefolds. And so this is really geometric reason why people care about these things. I mean, some people care about these things. So, but probably I don't have much time to talk about it. Anyway, so okay, so now we discussed, so what was the plan? The plan was to discuss, I gave you what the tensor product is supposed to give here, but then starting from that definition, from the definition oh, no, there's just a purely geometric construction. Of a solution of solutions to Young-Baxter. And this is somehow Davesh's Molex and I somehow modest contribution to the subject. I'm not going to discuss it here, but the upshot is that if you just trace what it says for in example 1, it's just going to give you this SL2 or GL2R matrix. And in example 2 was to give you a certain GL1 hat R matrix. And in general, for any Nakajima variety, it'll give you an R matrix associated with a certain Lie algebra, which is generally speaking strictly contain the corresponding Katsumori. But this gets little, slightly technical.
So you told me how to find V and V2.
Yeah, of two things, yeah.
But you haven't told us how to find R.
Yeah, that's there's some geometric construction. Maybe. Yeah. You can. This the reference for this is Davesh Molik and I wrote a paper about it. But I will tell you. So what I will tell you is that now, if I go. If I unwrap this definition, there's a general formula of how I'm going to multiply by. So what does this formula tell you about multiplication? So if I have.
Well,
Yeah, I don't know. There's so many important things on the board. I don't know what to erase. So this gives you, this construction in particular gives you so if I have, from this construction, you get the following formula for, if I have lambda, which is an element in second cohomology of X. So it's a divisor class on X. It gives you the following formula for the quantum product by this divisor. It starts as the cup product, and then come corrections. So corrections always have the following form. So you have a there's some kind of Planck constant from not so important. In fact, when I compare with this paper, it will be minus sign. It doesn't matter. And be a sum over positive roots of my Lie algebra. Okay, this is once I have the R matrix, then there is Lie algebra. It has a maximal torus, so I can talk about roots. So it's over positive roots of my Lie algebra, and then what comes here is the corresponding coroot q to the alpha, 1 minus q to the alpha. That's an element in the maximal torus. Torus of my algebra G, and the corresponding root operator E minus alpha E. And then, sorry, I forgot the more very important factor, which is make space for this. Here, this is the inner product of lambda with alpha. So this is, for finite dimensional Lie algebras, an expression like this, incidentally, is known in the work, in particular, it's called Casimir connection. This has been discussed in the work of Toledano Loredo, for example. So it's the reference for this infinite dimensional case is the work of Toledano Loredo. So, but let's see what it says. What this operator looks like in the case in this case. So we now want to talk about GL1. So what is the GL1 head? GL1 head is, I want to denote the generators of GL1 head by alphas. Therefore, I replace this by some other letter. Replace it by say eta. For GL1 head, etas are just integers. The corresponding roots are the Heisenberg generators. The corresponding, so we'll call it n. The corresponding root generators, this is in JL1, they of course commute. In JL1 head, there's a central extension that says the commutator of alpha minus n, alpha n, and alpha m. This is n times the delta function of n plus n. Which is that's the central extension in JL1 head. Then the maximal torus of my group is just one dimension. And so the operator I get here is sum, so this is the product with n. I can assume my lambda is also one dimensional. I can assume it to be 1. So it's a sum over n, q to the n, 1 minus q to the n, exponential minus n, minus, so maybe I'll take a new board. What we get is a sum over n q to the n 1 minus q to the n alpha minus n alpha n. This is for the quantum part. And when you compute the classical part, the result is very simple. But the way to do it is you form the generating function alpha z to be summation over n alpha minus n z to the n. And what you write here is, so my entire operator of quantum multiplication by the generator equals, so there's some constant which doesn't matter, integral of alpha cubed, plus some other constant which doesn't matter, integral of alpha squared, plus there's a contribution to this that makes this be, and some other constant. Third, 1 plus q to the and now we're supposed to recognize there's something, an equation in hydrodynamics. So what's a typical equation or quantum version of some hydrodynamic equation? What's a typical equation you write in hydrodynamics? Well, in one dimensional. So you write something like this: u t plus u ux, the transport equation, plus a linear operator of u. And the goal of this linear operator is to, so this is, the goal of this linear operator is that when at linearized level, you have a particular dispersion relation. That is to say, waves of a certain frequency propagate with a different speed. So that is to say that L, if I apply L to the exponential of say 2 pi I x, I want to be, x is now periodic, so I apply it to this. Well, I want particular relation, particularly this to be. So this means that wave with this frequency will propagate with the speed which is given by this. And in particular, say if you in KdV, there'll be the third derivative here. To say that this is one is the cube of the other. But more interesting thing, you study more interesting phenomena is this described by intermediate long wave equation, in which this function of n is, well, I times 1 plus q to the n over 1 minus q to the n. This describes hydrodynamic in some kind of two-layer liquid of a certain depth, and logarithm of q is the depth of that fluid. And then, sorry, there's n. There's also two derivatives, so 2 pi I n squared. And if you think of this equation, if you want to generate this equation with this Poisson bracket, then this should be your Hamiltonian. Okay, if you don't recognize it, then this is I'm saying if they, so this is here, if u equals alpha, and you want this equation to be Hamiltonian with respect to the Poisson bracket given by this, then the Hamiltonian should look like this. And so if you want the quantum version, here it is. And with this, and so with this, I don't know. Well, you can say, well, for example, this proves the thing that this is quantum integrable, which is of course well known. It's known, but it also constructs a generalization, which you can have a chain of this, you can have this in higher speed, and so on. But one thing I want to mention now, finally, maybe one new. So this equation, incidentally, of course, this is the quantum multiplication in Hilbert scheme of points that precedes the older recent development. It's a result of a certain history. So, but that's certainly this presents a new way of seeing it. And so now I'm going to finish with a statement about the spectrum of this operator. So now this will be this is a result of Nikita and I which is again, there's something we proved how at the dawn of this development, and so it's not exactly new, and we've been discussing it with Pavel over the years, and so well now I felt that maybe we should now would be a good time to review it, and so now so the statement would be the spectrum of this operator. The description of this beta ansatz, beta equation for the spectrum. Of quantum ILW. And so this is like this. So this operator commutes with the operator comes denoted del naught, the integral of alpha squared. And we now fix this eigenvalue. So fix the eigenvalue of this, eigenvalue to equal n, or maybe n if they're using, let's say k. Then there'll be k beta roots, so the energy, the eigenvalue, the spectrum E. This will be a sum of k beta roots, 1 plus xk, where xi solve the following system. Solve this beta equation. And the beta equation read, so maybe I'll use an auxiliary. Maybe I'll write it like this. So it's an equation I fix for any I take a product over J, a certain function we'll define in a second, as so all these constants there, they can be scaled somehow. They can be rescaled in different ways. In the end, the one meaningful constant remains, and it's in fact better to leave two constants, and you get better equations. So it'll be two constants, but it'll be homogeneous, so you can rescale it. So T1 minus T1 plus T2 minus T1 minus T. This is a comma here. Minus T2 of xi minus xj equals q times s T1 plus T2 over 2 over xi, where s of A1, A2, and so on x. This is the product of x minus ai over a product of x plus. And so it means, again, this is the theorem. It's not a new one, it's a pretty old one. And this is by Niemchenko. So, and the way it's proven is, the way it was proven, there's much more powerful technology available now, but it's through the study of this object here, which I didn't have time to talk about it, but it's maybe as I'm concluding this lecture, I'll tell you that on this side there's always some remarkable connection on the space of parameters. It says there's a flat connection on the space of parameters, which somehow, you can study as a remarkable non-stationary equation with the non-stationary Schrödinger equation with your integrable Hamiltonians, and a lot is known about the solutions of these equations. Somehow we know this solution of this equation better than we know the solutions of stationary Schrödinger equation in some sense. And so, but then from the asymptotics of the solution of this equation, you can easily read off the spectrum, and that's really what's happening here. And that's just an example. An example of the fact that to these equations of integrable equation of hydrodynamics, which somehow of great interest and been developed in the work of Pavel and his collaborators, they really fall in the same scheme as the finite dimensional spin chains, and they have the spectrum is described by something which is just like Wigman's old work on spectrum in finite dimensional spin chains. So that's okay. That's my hour, and happy birthday.
Questions? Well, if there are no questions, let's thank you very much.
Oh, there was a.
No,
sorry.
not really. Maybe it's a very stupid question. Actually, I will just want to ask, the Young-Baxter equation or the triangle equation, they have high-dimensional generalization by cohomological tetrahedron equation. I'm wondering whether there is something dual to this in your sense, whether your quantum cosmology can be generalized, linked to this.
Yeah, that'd be great. Yeah.
Stringy Baxter equation.
Yeah, that's fair. No, this I don't know yet. What is true, of course, is that it's just Young-Baxter is, it's just a relation in some braid group. And you see in the quantum cohomology, you similarly see more general braid group come in. So that those equations, like the reflection equations, certainly come in. But but that
some different dual language to describe Young-Baxter.
No, it's not dual. It's just a statement that in fact all the solutions we know can be realized from this, and it's sort of cool because here you get something. Here you get something more. You get something for which I wish I knew physical interpretation, namely a certain, some kind of connection on the space of parameters for the.
Why don't you do the same thing for tetrahedron?
Oh wow. Anyway, the idea was not to talk about the new work. The idea was to talk about old stuff.
Sorry, two short announcements. First, in common room 2P, the